So we'll take a more careful look at this as we go forward, looking at a bunch more slides about this, okay? So on the top, I just want to summarize from the last slide. We see the resting membrane potential of -70. It's going to increase to the threshold of -60. At that point, the voltage-gated sodium channels are going to open, allowing an influx of sodium. That is going to take the membrane resting potential of the cell, increase it to a much higher number, so it approaches 0. Then the next thing we see is that those sodium channels are going to close, and then the potassium channels are going to open, allowing potassium to suddenly rush out of the cell. And right, this is all happening in milliseconds. The potassium is going to rush out. As that does, the membrane potential is going to decrease. It'll hit the resting potential at -70 and go down a little bit lower, okay? Which is hyperpolarized when it becomes low like that. So I want to now jump to the bottom slide and give you a few more information. So the red line right here is showing how the sodium ion channels open and close. How sodium levels increase and then decrease. And then here how the potassium levels increase and then decrease, right? And this is due to the opening and closing of the sodium and potassium ion channels. Okay, so what happens in the beginning, right? We see the sodium levels going up and then going down. So we're seeing the gated sodium ion channels are going to open, and then guess what happens when you get to this very high level, which is going to correlate with the 0 membrane potential. We see the sodium ion channels are going to close. Okay, and then the sodium levels begin going down. What we see happening in the second red line is the potassium levels, right? So the potassium channels are going to open that are voltage gated. That leads to this peak level of potassium that is leaving the cell, right? Potassium level has left the cell. And then after the potassium is left, the potassium channels will become inactivated. They close, and then the diffusion of potassium is reduced, right? Because those potassium ions have moved out. And then we see at the end, both the sodium and potassium channels are closed. And after this hyperpolarization period, the sodium-potassium pumps that are functioning constitutively in all of our cells will restore the resting membrane potential, which is what you're seeing happening over here. And there's the cell membranes are loaded with the sodium-potassium pumps that are constantly pumping out 3 sodium and pumping in 2 potassium. So every action potential has the same amplitude. So what I'm showing you in the bottom is some stimuli that would be, trying to increase the membrane potential to be higher than -70. So this is a weak one. Nothing's going to happen. If it doesn't hit -60, it doesn't trigger an action potential. But let's say it does, right? So if it hits -60, then action potential will form. But however, if you even hit, let's say instead of just hitting -60, it went to -55 or -50. You know what? It doesn't matter, because you're still going to get the same strength of your action potential. The action potential amplitude does not change with the strength of the stimuli, because it's a threshold. Once you hit -60, you get the same effect, be it -60, -55, -50. And that was the all or none law. So the next thing I want to show you is the effect of stimulus strength on action potential frequency. So what we look over here, we see time on the x-axis and then strength on the y-axis. So if you have a very weak stimulus that doesn't hit the negative 60 millivolt membrane potential, guess what? You get no action potential at all. If you get a stimuli that does hit the negative 60 and you keep it on for a period of time, you will trigger action potential. So for example, you're getting 1, 2, 3, 4 action potentials with this particular stimulus. That would be, again, increasing the membrane resting potential. Increasing the membrane potential to be higher than that of the resting potential of negative 70. A stronger stimulus would, again, not change the amplitude or height of the action potential, but what they would do is they can change the frequency. So basically, a really strong stimulus, which would be, again, having a more dramatic increase in the membrane resting potential, would not lead to a greater amplitude of the action potential. What it would do would make the action potential be more frequent. So it'd be firing, take a break, firing, take a break, firing, take a break, which is what you're seeing with this pattern. So really the frequency is what will be more frequent with a stronger stimulus, and a weaker stimulus, as long as it passes the threshold, will give you a less frequent action potential. So why have those breaks, right? So like this slide, you see there's these gaps. Even with a strong stimulus, you're getting gaps between the time between each action potential. So it turns out that there is a refractory period, and the refractory period has to do with that ball and chain. At least the absolute refractory period has to do with the ball and chain that I was showing you with the voltage-gated sodium ion channel. So what we have in the x-axis is time in milliseconds, and then the y-axis we have the membrane potential in millivolts. Right? So here we see the stimulus has brought the depolarization from negative 70 to negative 55, right? That passes the negative 60, so an action potential will occur. And what happens is with these voltage-gated sodium channels is that they will be triggered to open when the voltage increases. After letting the sodium ions pass through, the ball and chain will go and block the channel, so no more sodium ions can travel through. And this is really happening during this absolute refractory period. So even if there's another stimulus, those voltage-gated ion channels are not going to open. Okay, and then after the period of refractory period, the ball and chain will move, and then the ion channel will regain its closed conformation. So there is also this relative refractory period, and this is the period where the exit of the potassium ions from the nerve actually reduce the membrane potential to be lower than negative 70. So maybe it'll go to minus 80, for example, right? And it'll reduce the membrane potential, making it hyperpolarized. So at this period, it's more difficult for a stimulus to be triggering an action potential, because if let's say here this was this gave the stimulus is able to increase the membrane potential by a unit of 15 millivolts, right? So it went from negative 70 to negative 55. So here, if we're down at negative 80 and it went up by 15, it would go to negative 65. That does not hit the threshold. So the relative refractory period is a period where, those sodium channels may be reactivated, but it's going to be way harder to get the action potential to occur, because the membrane potential is much lower than that of the resting membrane potential of -70. So again, here this threshold is really critical, and the axons I want to share with you have a cable property. So that what cable property means is that the sodium ions, for example, traveling down an axon will be they're going to be diffusing down the axon and traveling down it. However, the stimulus gets weaker as it travels over a distance, and that happens in cables, so we call it the cable property. But let's say you have something that at this position increase the membrane potential from -70 to about -60, right? As it travels further down the axon, the changes in the millivolts will be weaker and weaker as the distance increases from the site of the event where the depolarization is occurring. And you can do this, what they're showing down here is you can do this experimentally by taking an electrode and putting in positive charges to really do this experimentally. And those experiments are really important for helping us understand how nerve cells function. So I want to show you, again, a little bit more clearly how an action potential can travel down an axon. So here we have the axonal hillock over here, right, where there's going to be a depolarization event occurring, meaning that the sodium voltage-gated ion channels are going to open, right? Sodium's going to rush in. That's going to lead to this depolarization, right? This is the beginning of this action potential. And then what's going to happen is that this region that had brought in, had the sodium voltage-gated ion channels opening, they're going to close. And then the potassium ion channels are going to open. So, first we had the sodium rushing in. Then now we're going to have the potassium rushing out. Because the sodium in this first area of the axon is connected, touching the next area of the axon, there's going to be diffusion, and these sodium ions are going to diffuse into the neighboring area of the axon, right? And then that's going to hopefully be enough to trigger the change in the membrane potential in that next area of the axon, and then the sodium ion channels are going to open, right? Allow sodium to rush in. These are the sodium voltage-gated ion channels, okay? Then, after they close, the potassium voltage-gated ion channels are going to open, and potassium is going to rush out, right? And then, as these sodium ions over here are diffusing, going by diffusion to the next neighboring zone, they are going to then basically open the voltage-gated ion channels in the neighboring area, and then they'll open, then they'll close, and then next the potassium voltage-gated ion channels will open, and then potassium will be rushing out, right? And you can see this happening in each little segment of the axon. And you may be wondering how myelination could help with this process, right? Because you can imagine that this process is going to take a long time. It needs diffusion, right, to be happening, and this action potential needs to repeat every couple millimeters, right? It's a very small area that's being affected.